Today we are going to take a look at automatic differentiation. This is a way to, as you run your program, automatically get derivatives of the functions you calculate. And there's many things this is useful for. For example, gradient-based optimization algorithms. And one thing in particular that's very useful for is, or that is very used for these days is machine learning. So all of these machine learning libraries, they rely on automatic differentiation to find how the error function changes with respect to the input parameters. And today there's two ways to do it: forward mode and reverse mode. And today we'll look at reverse mode because there's a very interesting way you can do that. So let's make a new folder, and let's make that a workspace. So I think you would do like this. Okay, whatever. So we'll make one new crate that's called forward mode, and later on I will probably make it like a full-on workspace. All right, so what do we want to do? Forward mode automatic differentiation. Well, the idea is to, let's say we have some input value. Let's make it more concrete. So we have like some complicated function we want to calculate. It takes as an input a double, and returns a double. So it could be something just like x times x, as Copilot is suggesting. But it could also be much more complicated. Like it could be, now I want to do something. Can I do rust up ducks? And it, unfortunately, it doesn't have dark mode. Should have dark mode. Derivative with respect to x. Then we can say x instead goes to like dual x, which is the value of x, and it's 1. The reason it's 1 is because 1 is equal to the derivative of dx with respect to x. And as we start to apply more and more functions, we will always keep, so let's have some other value y, and that will become dual y, where the value is just y, and whatever we have over here will be dy dx. So for example, let's say that y is equal to x squared. Why not? Then dual y is equal to, again, x squared. And this is equal to dy dx, which is 2 times x. So how do you keep track of all this? Basically, we want to automatically calculate the second part, no matter which function we apply. And perhaps what we can do is, let's start by making a simple function that is just the power of x to some power, which we can even give that power here as well. So it's this, and we can calculate it. So let's say y is a complicated function, and the input is some x, which is 2.3. And well, let's make it something where we can actually verify it, and n is 2 as well. So now this y should be equal to 4, and dy dx should be equal to 2 times x, which is 4. And in general, we can also say that this is equal to n times x, n minus 1. So let's print this stuff. y equal y, and there we go. So we can run this function, run, and there's a bunch of warnings, but we can see here that y indeed does equal 4. We don't have the derivative yet, of course, so there's nothing to be done about that. Now the problem is, how do we, let's say we had this dual number working and whatever, so we could say down here, we could say dual x is equal to this thing that we talked about before. It's equal to the value and then the derivative with respect to x, which the derivative of x with respect to x is just 1. And then we could say, we would like to say dual f is just the dual x, and then maybe we'd also need a dual n, so we can make that. Let's make a dual n. It's again a float, and the value is n, but now n is just a constant, so the derivative is should be 0. So here's the problem. This function doesn't work with dual numbers. It only works with regular numbers. And as far as I know, maybe we can try to get Copilot to help us. Yeah, so we can just implement it for dual numbers or for regular numbers. Because there's no like trait, there's no number trait or anything like that. Only this like add and stuff, the basic operators are trait functions, but the rest is just methods on the structure. So for example, f64 has cosine, but f32 also has cosine. And yeah, it's a separate implementation. Which is makes our life hard, but what we simply have to do is say dual, dual, and dual. So you have to change your function a little bit, but it is what it is. So now this, of course, will not compile, and we don't want to print this, so we can print the value, and we can print dy dx is equal to the derivative, where we just get those numbers from the structure here. So of course, if we try to run that, it doesn't work, because okay, we still need x and n. Forgot about that. Let's put them here, and let's forget about this. Some of the expression fields have a method of the same name, so I wonder if you can just... Well, anyway. So what we need to do is implement this function, power of f. So let's see how it works. Okay, so the value doesn't change from regular numbers. So the value is self value power f with respect to n value. But now we have to combine the derivatives. So basically we have that we want to calculate y equals x. Well, in general we don't really know what we're getting here. It doesn't have to be x, so it could be y. Or let's even call it a. So it could be a which is a function of x, raised to the power of b, which is a function of x. So what is the derivative of that thing? The derivative of that thing is equal to should be equal to b times x. Now let's see, and then it should be equal to to this, but then we have to also multiply ddx of bx, and we also have to take the derivative with respect to a. Okay, so I think to make this calculation a bit easier for me right now, I'm going to write it in a different way. So we're going to have d dx, and it is indeed going to be this thing that Copilot suggests. We're going to take and put the logarithm up there. So need to do just adding some spaces so I can see what's happening. So that is equal to this whole thing. Sorry. Why can I not? There we go. So it's equal to that thing, derivative of that with respect to all of this. Let's put a bracket in there and a bracket there. So basically the derivative of all of this. And let's get it on a new line because there's too much. Times the derivative of the inner thing. But if you remember your kind of calculus, then if we say d of dx, e to the x is just e to the x. So the first part doesn't do anything. Lost track. Why is there a d here? It should be an e, I guess. First part doesn't do anything. The second part is, now we'll just write a tilde for like the derivative. It is the derivative of b times just the a thing, and then it is b times the derivative of then the logarithm of a, which is what Copilot is saying is this thing. So let me just do value here and then derivative, just to stop the complaints. So what do we have now? So let's say this is equal to a to the x, b to the x, and times, and there should be a bracket around that, times this thing. So we can actually simplify that a bit further. We can write b to the x. Well, let's do it a bit in steps. So I can multiply it out the parentheses, like so. And then here in the last one, I can actually simplify that by taking away that one. And then I just have this stuff. And over here, I don't think that can be simplified. Okay. So that's actually, it's actually more complicated than I thought, but I think it's correct. So what do we need to do now? We need to take the a, which is self, so self.value, power of f, n.value, times the derivative times self-value logarithm. So now we have done the first part, right? This part is all of that. So maybe we put it here and we can say like part 1 is that. So then I want to do part 2. So that's going to be the value, the power of f, the value of that. And this is just going to be part 1 plus part 2. So this is essentially how automatic differentiation works. It's automatic in the sense that when you use these numbers, you don't have to think about the derivatives. They're just calculated as you go along. Of course, when you implement the dual numbers, you do have to think about it, and it's not automatic. Nothing is for free, but when you use them, it's very easy. So now hopefully this thing should run. It runs and it gives us the correct numbers, but we can do better. We can actually write some tests. And how is it? You have to do like configure test or something like that. Then you have to say test. It's been a long time since I've written any Rust. So we can do this, and then I can say cargo test, I think, and it runs the test. Okay, so that is pretty good, but this is not a very good test. So we should write a test that does a lot of stuff. So maybe what do we call such a test? Let's call it test on a range. And X range is, how do you do ranges? It's doing it like this, but how do you do Rust range step? There's something called step by. Okay, that's interesting. So step doesn't exist. What is my Rust version? It should be older than that. Okay, you know what? So what we're going to do is we'll say let's take 10 numbers and let's map them, and we'll do this, and let's say X step is something like 0.1. Why not? So we take this as the F64 and then we multiply it by the step. So now we get like this thing. So let's do end step is probably whatever the same, and end range is also that. So now I want to say for X and X range, and for Y and Y range, N and N range, we're going to do some stuff. So we'll make first the dual X, then we'll make the dual N, and we'll calculate this complicated function, and we'll see here. This is kind of like a weird. Well, we can assert that the value is the same, that's fine. And let's make a finite difference derivative. So the idea is that we'll have like a y1, which is this thing, and y2 is just that thing, sure. No, sorry. So the idea is we can calculate the derivative of x by saying f, the derivative is basically equal to this thing where we step x a little bit, and we subtract what it was before, and we divide by the step size. So we also need to step here. Now, because this doesn't, sorry, I'm a little bit tired. So that should do it. And then we should say that this difference is quite small. The difference between the calculated derivative and the manual derivative. So let's say cargo test. And yeah, so great, Rust cargo, Rust borrow checker. Okay, so actually the test failed, which is very interesting. So when it fails, can we provide a message? Probably not. So let's get the stuff out of here, and let's call it just B for Boolean. And if not B, then I want to print some stuff, and here we can just assert. So the derivative is not a number. That's usually not good. Finite difference derivative is basically 0, which is weird. But perhaps this is because x is 0 and n is 0. Yeah. Okay, so why does it become not a number? It's probably because of the logarithm. We take the logarithm with respect to 0. We take the logarithm of 0, which is not defined. So how do we want to do that, actually? How do we want to do that? It's a bit annoying, so to get out of that, let's just say 1 here and 11, and let's run the tests. So actually I want to put the test down here. It's a little bit nicer. Okay, so now the tests pass, and we can even, like, let's do a lot of numbers, why not? So that actually failed. And here you can see that probably it's the finite difference derivative that is not good enough. So we can make that step size a little bit smaller. Let's see how that works. Still doesn't work. But now it failed in a different point. So here now it fails in 1.2, and up here it failed at 0.9. So I think it's simply that this is not quite accurate enough. So perhaps we need to do something like this. While true. So let's say next diff is, well, so next epsilon, that can be epsilon divided by 2. Then we can say the next y1 is that thing, and the next diff is that. And if the difference between the derivatives is smaller than this tolerance we have down here, so let's say accuracy tolerance, and accuracy tolerance, then we break. But otherwise we should say epsilon equals that. And I think here we can say this, and we can say it down here as well. So now we basically iterate. We iterate a couple of times to make sure that the finite difference thing has converged, but apparently that was not enough. So maybe if we do divided by 2. Come on. So anyway, so we'll always, like, it seems like there's always a problem somewhere. So I think what I want to do is let's not take this thing. Let's do like a relative. So next is, I think that maybe that's fine, but here in the comparison we'll say dual y derivative absolute value. So now we're saying if the, maybe we need to do it here too for consistency. So finite difference. So here we're saying if the deviation is less than 1%, we pass the test. Let's see if we can get that to work. At least it's not crashing right away, but I suppose we have like 10,000 things to get through, and this loop might end up doing too many steps. So let's do 1,000 steps at most. I think that's fine. Now it failed again. Now it failed very early, which is weird. Which is very weird. Probably because the derivative is very small. So you know what? I think what we're gonna do is, let's make it a loop again. We're not gonna do this many. Still it gets stuck in something, it seems like. It gets stuck, which is annoying. The thing is that this expression can also, there's also problems with doing this because finite derivatives are not necessarily stable. Finite difference derivatives are not necessarily stable. So how about we do this instead? So let's run it. It fails because the absolute error is because the absolute value is 0, so that doesn't work. So we're gonna do it like this. This can definitely be improved, but I think we spent too much time on it already. Okay, So I'm actually a little bit sad that this is not that complicated function, but still it ended up being a very complicated thing to do. So, because it has two arguments basically, let's take one that only has one argument. So I'm gonna get, well, maybe we just keep this for documentation. Okay, so let's do cosine, and it's gonna return a dual. And let's see, so we want to calculate cosine of x. Well, the value is easy, right? Value is just self-value cosine. What's the derivative? And actually this should be just some arbitrary thing. So what is the derivative of this thing? Well, it is the derivative of cosine of y with respect to y times the derivative of y with respect to x. This is the chain rule. So to construct the dual value, we simply need to say, okay, the value is the value, and the derivative is this thing, which is minus sine of y, times this thing, which we don't know what it is because it's y is an arbitrary thing, but we do have access to it because it's inside y itself. So we can say minus self-value sine times self-derivative. So I think, why don't we take this complicated now? Well, we do some stuff here, so I guess that's okay. But maybe in future tests, we don't need to rely on a function defined up there. So let's make another test. So it can be test cosine. And again, we want to test a bunch of things. And so the x step can be this, and x range can be this again. Here, maybe it's okay to start with 0. There's no divergence or anything. So let's say for x and x range, need to make a dual x. Dual x is easy. And here we assert on the value. So let's again do the finite difference thing. And Copilot is very handy here because it's very similar to what we had before. So let's run that test. And okay, it ran 3 tests, it just didn't show it right away. So that was a bit more easier, and that's because there's only one argument, so we don't have to worry too much. Let's write another test that lets us combine. So test combine cos and float thingy. So we can take Copilot's test, it's probably okay. So first we take x to the n, and then we take the cosine of that. So the derivative should be, it should be this thing. So we can actually calculate that ourselves like this, and then we can assert that those things are equal. So here we have the exact expression, so we can just assert that those are equal. Let's try to run that, and it also passes. So basically you can go through this procedure with all of these functions that you want to support, and it's pretty straightforward, if a little tedious. So let's have a look at these trait functions, because one thing we cannot do, let's make another test to show the problem. So test add add duals. So let's make dual 1 and dual 2. And this could be x, so we can say x is equal to 1. And here, and this could be some kind of y value, which could be 0, right? So we want to do this, but this is not possible right now. Cannot add dual to dual. But I think, if I'm not mistaken, we can just implement this trait add. We may have to import it, but so I think you do like this. So if I add 2 duals, I get another dual, and self plus another one. You just add the values and you also add the derivatives. So why do you add the derivatives? It's because d of dx, yeah, so it has already written it. So this is like the distributive rule for derivatives. And we cannot find add because it's defined somewhere. std ops add, so we have to say use std ops. And just for good measure, let's also get multiply. So how do we implement multiply? Well, it's like this. It's the product rule. So actually, you can just go here to Wikipedia, search for like product rule, and probably you can find these, like a list of these rules. But I think product rule, sum rule, and chain rule is all you need. But anyway, here you have it. The derivative of 2 things multiplied together is the derivative of the first thing times the other thing plus the first thing times the derivative of the other thing. So Copilot can probably do this for us. So the values are just multiplied, and this is like derivative times value, value times derivative. So now we can do this. And this is the value, and the derivative doesn't change. It's obviously not a very interesting test. So let's call it complicated add duals. What if we don't really know what they are? So we can say here's a dual x and the dual n we also need, and we can calculate this complicated function. Let's do another one that we say is dual x cosine. And that's annoying, so let's derive some things. All right. So now I can add them, and I can say the value of those should be x to the power n. Actually, why do we have this complicated function? It's a little bit silly, but let's do it like this instead, so we actually can see what's happening. And this is wrong, it should just be x. So let's try to run it, and it passes. But how about the derivative? But probably we'll need like some finite difference again, because it's hard to, it's too much to ask to calculate it, I think. So we basically want to calculate dual 3 for 2 different values. So here is, here it is. Here's the finite difference derivative. And then we can say the derivative should be equal to that, but that's probably not the right thing to do. So let's say that the absolute difference is less than this, like just like before. Let's run that, and it passes. We can do the exact same thing, just to check, with a multiply. And the values should be the multiplied values. And here we do the finite difference thing. And let's test that, and it fails. It fails, it fails, it fails. Let's print some debug information. Okay, so that really fails. So it does seem like there's a bug somewhere, but there's no bug here, so could be in the test. And that's the problem. And now it passes. So as a final thing, let's get rid of this complicated function, which is just x to the power n, to make everything a little bit more readable. So that warning doesn't really matter. So there you have it. I hope it makes a little bit of sense, but if nothing else, maybe you can be inspired to go read about it. So basically, just by implementing this simple struct and these admittedly somewhat complicated expressions, but maybe you can get Wolfram Alpha to do it for you. And these traits, then you can calculate very complicated things and their derivatives quite easily. So that is one way to do automatic differentiation, which you can use to, if you have some complicated function, you want to optimize it, you can use the gradients, the derivatives, to help you optimize it. So we might in another video look at reverse mode differentiation, which has the property that is very computationally efficient to calculate one output value, but the derivative of that output value with respect to many variables. Forward mode has the property that it's very easy to calculate many output values and their derivatives with respect to a single input value. Basically the one that you set to 1 in the beginning of the calculation. So yeah, I think that's gonna do it, and I will see you in the next one. Bye bye.